There are three kinds of problems in this world: easy, hard, and impossible. NP-Completeness is about a kind of very hard problems, although not the hardest. So we're gonna see what NP means. By the way, what's your guess? Non-polynomial? Not really. Let's recall that in the fundamental course, we have discussed problems like Euler circuit problem. That is to find a path that touches every edge exactly once. And that is a very simple problem that can be solved by DFS, right? Depth first search. And there's another one named Hamilton cycle problem, which looks quite similar to the Euler circuit problem. Is to find a single cycle that contains every vertex. And this one is quite hard. So this is an easy one, and this is the hard one. Okay, another pair of problems is like single source unweighted shortest path problem, and which can be solved by a simple BFS, breadth first search, right? And there's another one called single source unweighted longest path problem, which is a very hard one. So that's the easy one, that's the hard one. And being hard means there's no known algorithms that are guaranteed to run in polynomial time. But again, NP doesn't stand for no polynomial. And among all the problems, we have the easiest ones that can be solved in linear time. We say that with linear time complexity, it ought to be the easiest problem because we have to read inputs at least once. And that will be big O of n already, right? And the hardest ones are the mission impossible. They are called undecidable problems, which means there are some questions that we simply cannot answer. We cannot answer yes, nor can we answer no. In the year of 1900, the greatest mathematician David Hilbert announced in the International Congress of Mathematicians his famous 23 research problems to be investigated in the coming century. And one of the problems is the question of decidability. Could there exist, at least in principle, any definite method or process by which all mathematical questions could be decided? And by the time he posed this problem, he was quite optimistic about the answer. So he made that very famous statement saying that what we want to know, we will know. However, 31 years later, Kurt Gödel proved that not all true statements that evolve from an axiomatic system can be proven. In other words, we can never know everything nor prove everything we discover. So basically, what he proved was that we can prove something based on the current axiomatic system, right? And this system contains finitely many axioms. But this system is not complete. Means that there's always something out there that cannot be proved. Then you may say that, hey, why don't we simply collect it into our system, right? If we cannot prove it, just define it to be true or false and accept it as a fact, right? Well, yes, we can do so. So whenever we encounter something that we cannot prove, just collect it as a new axiom. It's okay, but Gödel has proven that this procedure can go infinite. Means no matter how many axioms we collect, there will always be something that is out of our range. So there's always something that we have to believe from the bottom of our hearts, even though there's no proof. So one famous impossible, say undecidable problem is Turing's halting problem. The question is it possible to have your C compiler detect all the infinite loops? And the answer is no. So halting problem is undecidable. We can prove it by contradiction. Say if the answer is yes, if there exists an infinite loop checking program, then surely it can be used to check itself, right? Now let's consider a program like this. This function loop would accept one program P and check if P of P loops, we print yes. Otherwise, we go to infinite loop. So what do we get here? What will happen if we let this loop check itself? Then we have two possible situations, right? One is that if it terminates, then the second line is true, and it will go infinite loop. So it loops, right? Or if it loops, then the first line is true. Then it will terminate and print yes. So here comes the contradiction. So what's wrong? Which part is wrong? The wrong assumption is here. That's if this one loops, it's actually impossible to tell whether or not this function will loop. Or in other words, if there is one function that can tell if this statement is true or false, then we're going to end up at this contradiction. So this is impossible. And the impossible problems, so say undecidable problems, are the hardest ones. And among those solvable, decidable problems, we have the hard ones in class NP. NP is defined by Turing machine, which was invented by Alan Matheson Turing, who's known as the founder of computer science. And if you're interested in his life, you can check out his website after the class. All right. So the task of a Turing machine is to simulate any kind of computation, which a mathematician can do by some arithmetical method, assuming that this guy has infinite time, energy, paper, and pen, and is completely dedicated to the work. And the Turing machine has two components, namely the infinite memory and a scanner. The memory is an infinite one-dimensional tape or several tapes divided into units. That one corresponds to the data storage in our modern computer. And the scanner is a finite state controller that will control head movements according to current state and the symbol that the head is pointing to. So this part corresponds to the instruction storage in our modern computer. And the operations are, so we have several tapes, and each tape has infinite many of units. Okay, and we have one scanner that has many heads, and each head points to a unit at one tape. Okay, and we say one head can point to one and only one unit at each state. It may move at most one unit to the left or to the right. So the first operation is that we can change the finite control state. And next is we can erase the symbol in the unit currently pointed by the head and write a new symbol in. And we can move the heads, and each head can move one unit either to the left or to the right, or stays at its current positions. So with this simple structure, we can let this machine to do a lot of complicated works. We have two different kinds of Turing machines. One is a normal machine, we say, a deterministic Turing machine. this kind of machine executes one instruction at each point in time. Then depending on this instruction, it goes to the next unique instruction. So we can understand the deterministic Turing machine as a normal machine that can solve a problem step by step. And another kind of Turing machine is like a magic box. It's called a non-deterministic Turing machine. It's free to choose its next step from a finite set, and if one of these steps lead to a solution, it will always choose the correct one. So it's an extremely smart Turing machine. So it's like a magic box. If there is one solution, it will always smart enough to choose the correct one. On the other hand, no matter how smart it is, undecidable problems are still undecidable. And NP means non-deterministic polynomial time. A problem is in NP means it can be solved by a non-deterministic Turing machine in polynomial time. So in other words, the problem is in NP if we can prove any solution is true in polynomial time. Means that if we can tell whether or not it is a solution in polynomial time, then the non-deterministic Turing machine will be smart enough to choose that one and solve the problem. So in short, the class P means the set of problems that can be solved in polynomial time. So class P is easy to find, and NP is easy to check. For example, the Hamilton cycle problem is to find a single cycle that contains every vertex. We say it's easy to check because given any graph, we can find a simple circuit in polynomial time, right? And to answer the question, does this simple circuit include all the vertices? To answer that question, it only takes a linear time to check if every vertex is included in this simple circuit, right? So if that can be done in polynomial time, then this problem can be solved by a non-deterministic Turing machine in polynomial time. And therefore, this one is in NP. However, it doesn't mean that all the decidable problems are in NP. Okay, for example, consider the problem of determining whether a graph does not have a Hamilton cycle. Right, so we say that NP problems are hard problems, but comparing to the hardest ones, they are relatively easy. At least they are easy to check. So obviously we have that P is in NP. Means if we can solve it on a normal deterministic Turing machine in polynomial time, certainly we can solve it on a non-deterministic Turing machine in polynomial time. But the big question is there any problem that is in NP but not in P? Well, we do have many NP problems that so far we still don't know how to solve them in polynomial time. But it doesn't mean that the polynomial time method doesn't exist. It could be that we're not smart enough to figure it out, right? So, so far, no one knows the answer. So it's still an open problem, and maybe it's waiting for you to solve it. Till this day, computer scientists have managed to simplify the problem a little bit. They have defined the hardest problem set, the NP-complete problems. Well, here I put the hardest means they are the hardest among all the NP problems. Okay, and an NP-complete problem has the property that any problem in NP can be polynomially reduced to it. Means that we can convert any problem in NP into this problem in polynomial time. And what is that supposed to mean? It means if we can solve any NP-complete problem in polynomial time, then we will be able to solve in polynomial time all the problems in NP. So it means that among all those NP-complete problems, if you can solve just one of them in polynomial time, that means you can solve all of them in polynomial time. Then for sure, your name will be printed in the human history. Now let's define it in a formal way. Say, given any instance alpha in problem A, if we can find a program that maps this alpha into another instance beta in problem B, with the time complexity being polynomial, and another program D that solves this instance beta, and to get an answer in another polynomial time, and more if the answer of beta is the same as the answer of alpha, then what do we get? We get that for any alpha in the problem A, let's first try to convert alpha into beta, and then try to solve beta, and get the answer for beta. And if the answer for beta is equal to the answer for alpha, then solving beta is equivalent to solve alpha, right? If the time taken to make this conversion is polynomial, and the time taken to solve this problem is also polynomial, then the total time for this procedure is polynomial. Therefore, we can solve this problem A in polynomial time and obtain the answer, right? And usually there are two versions for an optimization problem, the normal version and the decision version. Decision version means to simply answer yes or no. For example, say the shortest path problem can be stated as this. Say, given a directed graph G and a pair of vertices U and V, we're supposed to find the shortest path between U and V, and this is the normal version. The decision version can be stated like this. Say, given a directed graph G, vertices U and V, and an integer k, is there a path from U to V consisting of at most k edges? That's the decision version. So you see that these two versions are actually equivalent. Means if we can find the shortest path, then we know the path length, right? So it will be trivial to answer the question for any k, right? And on the other hand, if we can answer the question for any k, then we can increment the k, right? Starting from 0, where the answer is obviously no. And then let's try increment the k to 1, to 2, to 3, and so on. The first k, which gets yes as the answer, is the shortest path length, right? So if we analyze the normal version of the problems, it will be difficult to set the equivalence between two completely different problems, right? But if we concentrate on the decision versions, it suddenly becomes simple, because the answers for both problems will be just yes or no.